hit the button. All right, and so just kind of looking ahead, we're at the business. Normally I don't stick this all in the live stream, but let's look at some business end of things here. So we are, I think you just took this quiz right here. Resistance, resistivity, and temperature. All right. All right, so there's that. And it sounds like people are saying if you refresh your Canvas page, then the grading will get it correct. So it sounds like you need to hit refresh, hopefully. So try that. All right. But now getting back into here. So we just finished that. I want to look ahead and you can see something here. We have an option here. And I think I know the answer, but I'll just mention it to you. So this is next week. Notice the following here. I want to point out this. So we have no lecture quiz next week. We finally made it to that break. All right. And let me see if I can make this just a little smaller so I can, oops, get everything on the screen here. There we go. All right. So if there's extreme passion about this, we could discuss this. But notice the following week, you have a quiz on RC transients. And notice there's a lab quiz here on RC transients the week before. So the reason I wanted to push off this quiz to next week was so that you could do the lab first, which I thought would be a good thing. Now, something I realized here is as soon as we get to this week, this would be a good time to check yourself with a practice test. So if for some reason the class was extremely passionate about this, I could take this quiz and move it up here to a Wednesday, to next Wednesday if you wanted. That way you have no quiz during this week. But to be honest, I don't think it's worth the effort of moving all that stuff around. So, I mean, most students would rather push off quizzes as long as possible, even if it hurts them. They just are willing to do any kind of crazy thing. But what this does mean is you're going to have a quiz next week, and then I'm going to expect you, let's see. Sorry, next week you have no quiz, and then the following week you have a quiz, and sometime in there I want you to take a practice test. So you could see that there's going to be a lot of work in this week, but not as much work in this week. So just make your plans accordingly. All right. So it looks like week 10 of this course is going to require a little bit of extra, and week 9 of this course, not so much. So that's next week. All right. I hope everybody is aware of that now. All right. So if you have questions about that, you can, at least next week, you get a little bit of a break. Hopefully you get ahead in every other course or get ahead in this class. That way you have time to put in that practice test the following week. All right. I don't see any reason to bump up the quiz.
I've got a quick question.
Yeah, go for it.
You were suggesting us to take a practice quiz. What exactly is the practice quiz?
Sorry, a practice test.
Practice test, sorry. Yeah.
Just to get you ready for the final exam.
Oh, for the final. Okay. I thought maybe there was a midterm or something coming up that I didn't notice. Okay.
No. And my thought was it's probably better to take a practice test every 4 chapters rather than to try and do all 12 right before finals. And so, yeah, just basically give yourself 2 hours to take one of those practice tests. That way, when the final comes up, you've kind of studied a little bit already. And so the practice tests are 4 chapters, and that gives people that haven't had me for class before an idea of what a paper test would be like. That way they can know early before the drop deadline if they're like, oh man, these tests are hard.
Yeah. If that's the case, you should do more than one, definitely, as someone who has taken you before.
Absolutely. So, and I mentioned that in that link. I'm like, the first test, usually you're like, geez, I suck. And then the second one, you're like, oh, I'm slightly better. And usually the third one, you're like, oh, actually, I do know something. So with the practice tests, yeah, all of them for sure. If you take 4, you're going to get an A. If you take 3, you'll probably get a B or a C. If you take 2, you might get a C or a D if you're lucky. Yeah. But the idea is take some as you go along. That way, when the final comes, you're not taking all the practice tests at once, because that would really suck to spend your whole Thanksgiving doing physics. Actually, that sounds great to me. Doing physics is a lot more fun than writing Canvas quizzes. All right, there's that. Yes, for sure. All right, and then regarding the regrading, let's give it some time and see what happens here. I don't know. I got a message saying it was done, but I have no idea. All right, so where were we last time? We talked about so let's get into that.
Really quick, I actually found out about the regrading.
Yes.
The regrading only happens for people who have submitted before you hit the regrade. If you hit if people submitted after you hit the regrade, those are the people who are it's still gonna be wrong for them.
So wait, if they submit it after the regrade. Oh, okay. Well, let's talk about that on the break or something. Yeah. Sounds like there's something tricky there. All right. Last time we were doing some of these problems, and it sounds like that's going to be the insight I need to understand it. But we were looking at some of these weird ones in here. And so a lot of times on a paper test, I'll do a question like this one or like this one. And so I'm going to go ahead and let you use the lecture from last time to do those. And most of the time, these seem kind of simple. I do want to point out this one is where you see how they could be tricky. So definitely do this 27.5, and you'll see that it's counterintuitive. And I think we finished there last time. That said, scrolling down to the next page. So looking at 121 in the workbook, 27.6 and 27.7 are slightly interesting for this reason. It's interesting to see what happens when you put batteries in series or parallel. And so that's what these questions are about, 26.6 and 26.7. I'll be straight with you. I tend not to put a question with 2 batteries in series or 2 batteries in parallel like these two on any quizzes or tests. So if you're looking for problems that you just need to kind of read over and learn a little bit about, but not spend a lot of time, that's 26.6 and 27.6 and 27.7. These 2 problems, just follow along with the solution and read and learn a little bit. And then I'll tell you more after we know about KVL, how to handle this. But these are interesting and some of them are dangerous. So yeah, let's leave it at that. All right. Let's maybe start here and take a look at this problem. Yeah, you could light fires with those things. So I'm going to look at 27.8 and just talk about this one. All right. And this will be kind of a review from last time. All right. So in these problems here, we've got a battery, and I'm going to kind of draw the battery as this. In the real world, batteries have resistance as well. Okay, capacitors do too. Right? There's always some resistance between the 2 plates of a capacitor, even if it's the resistance of the air gap. So, whoops, I don't need a box around that. So in this case, I want to call this the internal resistance, little r, of the battery, and this is big R. And now you might be saying, what about the wires? The wires have resistance too. You're absolutely right. We could bundle in the resistance of the wires with this here. And so the idea is to take a real life circuit and model it correctly, what you do is you say, we're going to either ignore the resistance of the wires, or we can, and ignore the resistance of this battery, or we can bundle it in and say we have ideal batteries with voltage E that have 0 resistance, then put all the extra resistance from wires, internal resistance, whatever, into something else and call this little r. All right. So in this case, this is equivalent to a circuit with an ideal battery with no resistance and a resistor over here of size, in this case, if we have little r and big R, are these two in series or parallel here?
Series.
Series. So this would be, do I do the 1 over thing or just add them up for resistors?
Add them up.
In series. Add them up. So we've got R plus R, and in this case. So now, once I know this situation, I say, aha, I have one circuit element in parallel with the battery. I know that this one has the same voltage as the battery. From there, I could say, aha, well, now that I know the voltage and the resistance, I know that from Ohm's law, if delta V equals IR, I know that I is equal to delta V over R, which in this case is E over R plus little r. And now, coming back to here, which thing can I bring back to this circuit? Is it the voltage or the current that these things share?
Current.
Current. So in this case, I would equal E over R plus little r. And so notice that the voltage across this one is not E. And that was the point. The idea here is if in the real world you use a battery, the voltage of the battery, when you measure it with the DMM all by itself, is not the voltage that gets applied to a load resistor. So it turns out the applied voltage is going to equal, well, it's I times R. So it's going to be, in this case, let me write it like this. And I'm just going to put capital R here. Take a second and make sure you feel okay with that. The idea here is there's the current times the resistance. Voltage equals IR. I wrote it in this weird way because I don't know if you can notice, this has no units and that has units of volts. This is a famous equation. This is called the voltage divider equation. Now, my point here is this. All this time we've been talking about batteries and we've been drawing them as these little script E's and ignoring any internal resistance. It turns out if the internal resistance is small, then notice this is approximately equal to the full voltage of the battery. So in practice, as long as your resistors are more than 10 or 100 ohms, usually this internal resistance of a battery is negligible. So if the internal resistance of a power supply could also be involved in some of your lab experiments, right? And so if you're curious, I made videos of different resistors connected to the power supply and to a battery. And from those, you can get an idea of whether or not the internal resistance is negligible or not, and approximately what value. You could tell this, if you just keep using smaller and smaller load resistors and just keep measuring the voltage of this resistor, at some point, you're going to see that the voltage across this is exactly half. Well, at that point, the load resistor and the internal resistance must be about the same. So if you just keep sweeping the resistance here using different resistors until the battery's voltage appears to cut in half, you'll know that's the internal resistance of the battery. All right, or you could just plot it and do a slope or all kinds of different things. So just wanted to point out that fact. Any questions about that particular fact? Batteries have some resistance too. This circuit describes how you might learn about that. That was the goal of this. Sweet. All right, let's see what's next. There's a little bit more work to do in there. And actually, this is kind of, there's one thing that's slightly cool, especially for you electrical engineers or maybe physics majors. At this point, you could actually plot this function. You could get the power here too, right? So power would be I squared times its resistance. And notice you get this weird function in here. And what you could do is you could plot the power delivered versus the resistance. And it turns out If this resistor is really big, you don't get much power transfer. Why is that? Well, if the resistor is really big, you get a small current. If this resistor is really small, well, then this term is really small. And so there's this trade-off. If the resistance is really big, it looks like it's going to be big, but the current is tiny. If the resistance is really small, the current is big, but this value is really tiny. And so there's some special spot where you get the maximum power transfer. You get maximum power delivered from the battery to the load resistor when these two happen to be exactly the same size. And so that's a version of what's known as impedance matching. And I'll let you do the problem. So that's kind of the interesting part of this. And maybe I'll just show you where that shows up. So if you go through this problem, this is some good stuff. You can determine the power and you can figure out which one gives you the maximum power transfer. And I made some plots so you can see it. And so if you want to try and understand what this is all about, that's great. I think we beat that one to death. I'll let you do the calculus at home on that one. So this is a classic problem. It's in almost every physics book. You should learn about it. And impedance matching is a topic that shows up in all kinds of stuff. All right. Ooh, a Wheatstone Bridge. This one's kind of sneaky here. Maybe let's look at this one and try and analyze the circuit. All right. So I'm looking at 27.9 and I'm going to read about this one. All right. I'm just drawing it really quick. We see a variable resistor here. So maybe you've heard of a rheostat or a pot, a potentiometer. These things are all kind of related. The idea is if I could, let me get back into here. So we have a sliding contact here. Imagine wrapped around a cardboard tube. Well, what you could do is you could literally drag a connector across the wire and basically connect at different lengths. From our experiment last week, as you change the length of a wire, you change its resistance. So the idea is you basically drag this little sliding contact along a coil of wire and make contact at a different point. You can adjust this resistance. Now, in this particular case, what are we supposed to do? I got to read this again. Just getting my book here. All right. So this device is known as a Wheatstone Bridge. All right. Okay. And so what we're going to do in practice, you put an ammeter here, which is not shown. And the idea here is this. You keep sliding this until this measurement reads 0 current. Well, if there's no current flowing that way, then this is effectively not even there, right? Nothing's happening. So again, you start out with the ammeter in place, you're going to slide this back and forth, and at some point, this current is 0. At that point, you could take this portion out of the loop and it shouldn't change the circuit since no current is flowing there. Okay, that's the issue. Well, now we could see that in this circuit, I'm going to try and draw the equivalent down here, and maybe you do what you think it is. So I'm going to draw what I think the equivalent of this circuit looks like. And it might take me more than one step, might take you more than one step. And then here, these ones are in parallel. I'll just call this RZ for just, I don't know what reason. And so for me, RZ is going to equal man, I'm running out of room on this tiny little whiteboard. It's going to be this resistor times this resistor all over the sum of all those. Whew. And then down here, you can see you'd have to add in the equivalent resistance is equal to RZ plus R naught. And we're starting to get kind of messy here. But maybe I'll just wait for a second. Just like the capacitor chapter, we need to kind of figure out the equivalent resistance in this circuit before we can work our way backwards and learn something about the current and the voltage, etc. So in this case, I said, okay, these two are in series and these two are in series. So I'll combine these two in series by just adding them together. I'll combine these two in series by just adding them together. Now these two are in parallel, so I'll do that parallel rule to figure out that one. And then finally, that is in series with that parallel combination. I can spit that thing out. And let's go look in the book and see if it's more organized in there. Where are we here? There's that power one. So notice this is that graph. And then, oh, clever way. There's a clever way and a long version of this one. So the long way is what I just started working on, right? You can see I just started doing all this. And notice how long this gets. Ugh, blah, 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 blah. So maybe I should actually read the question and see what I was trying to do. But you could see you could work this out and figure out this resistance. All right. That was what we're trying to do. Aha. So now let's go back and look at this clever way and see that sometimes doing the brute force method is kind of painful. So let's go back and see what we were trying to do. We're trying to figure out the value of little r from this, okay? So, all right, so we see that trying to be not clever, we just did all this work and it could work out, right? We could figure out, okay, let's work our way backwards. But let's go look at the clever idea, all right? So, and now what we're going to use is, if I could, let me show you something. Let me tell you what the clever way is. Okay, we know these sets of rules here, right? So we know that we're doing series and parallel. We know this set of rules applies. So the idea is rather than trying to always figure out the equivalent resistance all the way down and then work all the way back up, maybe we can use some of these little tricks where in parallel things have the same voltage and in series things have the same current. If we could use those rules, sometimes it saves you a lot of math. All right, so clearing that and then going back to here, let's look at this solution. All right. Let's see if this makes sense. So we know the voltage across this branch has to equal the voltage across this branch because they're in parallel, right? Two things in parallel have the same voltage. So that's what this sentence is telling us. Furthermore, no current flows. So that tells us these 2 points are at the same voltage. So again, what that says is the change in voltage across 1 is going to have to be the same as the change in voltage across S if no current is flowing, right? Because think, if these 2 points were at different voltages, current would flow through that wire. There'd be a potential difference there. This is really clever. So I guess in short, you know this. And so once you know that, you can take these ratios and see what you get. Finally, in series, we know these things have the same current. So that's going to allow us to drop out these currents like that. And oh my gosh, that's so much faster than doing the whole R equivalent and working your way back. If you don't see that, the other method still works. This is a famous physics problem as well, the Wheatstone Bridge. So they're both good to do. You could learn a lot from doing that. And I maybe I'll pause here. What are we trying to do here? We're trying to learn how to use the ideas of series and parallel and how that affects resistance, current, and voltage. And so the idea behind this problem is to show you sometimes if you're clever, you could use the rules of same voltage or same current to avoid having to do all that REQ work. However, that long process of going all the way down to REQ and then working all the way back up should always work for you as well. It may be a little bit longer, maybe 5 extra lines of work. So, but that said, that was the goal of this problem, was to show you sometimes there are shortcuts. Questions about that?
So
I think I'm. Oh, go
ahead.
for it, Trey. You go for it.
Would that basically mean that little r is equal to R2 since the resistances everywhere else are the same?
No, it ends up saying the ratio of these two has to be the same as the ratio of those two.
Ah, okay.
Right? So think about it. These two, well, right? Like let's say this was 3 and this was 5, right? This one could be 0.3 and this one, whoops. So if this was 3 and 5, this could be 0.3 and 0.5. And so typically this is done with very small resistances. And the idea is it's very hard to measure small resistances with a DMM. DMMs can only read resistances to approximately 0.1 ohms, maybe 0.2. And so you can't get multiple sig figs. This is a technique that allows you could very easily figure out many sig figs on a long skinny wire by doing the experiment we did last week and knowing the resistivity and the length and blah, blah, blah. So you could actually get a whole bunch of sig figs on this. These could be large resistors, fine. And then we'd find out, aha, when I get this just right, I see that no current flows here, and I can get this from a ratio of something that has a lot of sig figs, a lot of sig figs, and a lot of sig figs. This technique is used for measuring small resistances accurately without having to do those crazy things that we did last week. What would Horatio do? Definitely take a ratio. Yeah, Trey, is that good on that?
Yeah, it is. Thank you.
It's the ratio that's the same. Ryan, what was your question?
Yeah, Trey's question was part of it. I guess my other part of my question was maybe could you elaborate conceptually, I guess, the idea you were saying the currents are the same and so, or there's no current.
Yeah. Okay. So
And so
let's say you put a wire here. Shouldn't the resistance of this wire be rho L over area?
Yes. Yeah.
Right? Because there's some resistance to every wire. So if you just put a wire here and then you put an ammeter in here, right? The resistance of this would be some small amount. You're okay with that? It wouldn't be 0, it'd be some small number.
Yes.
What's an
Now,
ammeter?
an ammeter is a DMM set to measure current.
Thank you.
Yep. So that's why they call it a DMM, digital multimeter. It's called a voltmeter when it's measuring volts, and it's called an ammeter or amp meter basically when it's measuring current. So the idea here is if you put this in here, this has negligible resistance. It should be very easy for current to flow. So if you have these things imbalanced at all, at some point you're going to have some voltage here and a different voltage here. So there's a delta V across this resistance, current would flow, right?
Interesting. So you're saying that would be kind of like create its own little circuit right in there.
Yes.
Okay.
Now, that circuit would be much harder to understand because it wouldn't be series. It wouldn't be parallel. Is there any possible way to compute that? Oh, that's right. The last half of class today will explain how you would handle circuits with triangles in them. So it's a foreshadowing as well. But for right now, we're going to put it in here and assume that there would be no current here. And if you have no current, and if this is a resistance, this is what I'm saying. If I is equal to 0 and there's some tiny little resistance, let's call it R twiddle. Well, delta V is equal to I times R twiddle, right?
Mm-hmm.
Well, if delta V is 0, I know R twiddle's not 0. That would mean I has to be 0. Or vice versa. If I is 0, that means the potential difference has to be 0. The difference in potential means this voltage minus that voltage.
Mm-hmm.
Yeah. Now,
okay.
Yeah. If it helps, imagine I put in some numbers in a circuit, right? And I do this in some of the future problems. So I'm going to do this, but let's say you pick a point that's 0, like a gravitational potential energy problem. That's 0 volts. So this spot is at 0. This spot up here might be at, say, 1.5 volts if we used a 1.5 volt battery. Delta V would be 1.5 volts across this battery. This spot would be at 1.5 volts. This spot right here would be at some other number. Let's say it's 1.3 volts. It's got to be less than 1.5. This spot down here would be at 0 volts. And what I'm saying is maybe this spot is at 0.6 volts. And this spot over here is at 0.6 volts. So the node voltage, or the voltage at one particular spot at one particular node, is 0.6. The change in voltage going from this node to that node is 0. Is that helping, Ryan?
Yeah.
Yeah. More
and that
on
kind
that in future problems too.
Yeah, definitely. And that kind of brought up also another thing I was thinking about. So just because those two nodes are both 0.6, let's say, that doesn't mean that R1 and RS are the same value for resistance.
Right.
Okay.
R1 and RS could be totally different numbers. Yeah.
Interesting. Okay.
And so what's the deal here? Let's say these were 10 times smaller. Well, then you would expect 10 times more current to go this way than that way. And as a result, the change in voltages are the same. You have 10 times less resistance, but 10 times more current. The delta V's are the same.
Oh, okay.
Yeah. And so if you don't believe me, you know Tinkercad, make a Tinkercad just like this and put resistors on here that are 10 times bigger than that side. And then you can put your multimeters on there and measure the voltages and see they do have the same voltage drops.
Gotcha.
Is that cool?
Awesome. Yeah.
Yeah, so that Tinkercad is a pretty good simulator, or you could use the FET. You could type in DC circuit FET. So yeah, all right, that's good stuff. And this is probably a good time to take a quick break. And let's see, there's more questions. Yeah. Oh, so you would make up your own resistors there. Yeah. So if you're going to make a simulation of this, what you could do is you could put some random small resistor here and measure the voltage across it. And instead of using an ammeter, you'd basically be using a voltmeter. And you'd say, okay, make this, just keep adjusting this resistor's value, like by typing in the numbers in Tinkercad. So you could pick numbers for this one, this one, this one, this one, and this one. And this one, you just play with the number until you get no voltage across the middle one or no current through it. Is that good? That's how you would Tinkercad that. Yeah. All right. Cool. All right. So let's go ahead and take a quick break. Yeah. All right. I'll use the restroom and I'll be right back. So maybe about 8 minutes or something. Okay. All right. Oh my goodness. It's always brutal having lecture right after a quiz. It's just not great for you guys or for me or for anybody. It's just like you guys are all just so excited about the quiz. I'll say it that way. But man, it's so hard for, and it's like, oh my gosh, 60 people with 60 different quizzes trying to ask me everything all at once. It just makes me want to run away and smash something. So yeah, I appreciate you guys having to be patient and wait till office hours. And it's just like, I know that's all you want to think about, but what are we going to do? So that said, let's get back into it and talk about something that's a little bit, this is actually going to be maybe a little bit exciting here. So we'll work on that later, Nate Dogg. I'm working on that one. All right. So, all right. Let me motivate something for you here. All right. Let's say we had a circuit like this. Just like this.
Yeah, I thought we weren't doing extra batteries.
We weren't doing extra batteries like those two questions. So yeah, 26.6 and 26.7, we don't do extra batteries. But once I show you this new technique, handling extra batteries will be actually a lot easier. It's very systematic. And so this one, you can see it's very complicated. Up till now, we've ignored multiple battery circuits. And what about this thing? If I label these, let's say this is R1, R2, R3, R4, and R5. So look at, in particular, at resistors R3, R2, and R4. Are they series or parallel?
Series.
Jay says both. Somebody says series. Any other thoughts?
You're asking about which ones in
these three, series
three?
or parallel? Somebody said series. Somebody said both.
It's none.
It's neither. It's not series. It's not parallel. How can we deal with this? So there's a couple of ways you could do it. One is you could use Google and you could look up what's called a delta Y transform or a delta star. And what that does is it changes this triangle into a Y shape, which then will allow you to do the circuit. And that's an electrical engineering trick. We're not going to learn that trick because it's a little bit complicated. We're not going to do sometimes it's also called a delta star transform. But what we can do is this. This is the big picture. Watch this right now. If you're a little tired, a little faded, I'm going to give you an idea of how we're going to handle this. I see three distinct loops. This is a little bit like what Ryan was talking about earlier. I could say there's a loop here. I'll call that loop 1. I could say there's a loop here. I could call this loop 2. And there's a loop here. I could call that loop 3. In addition, I could label some currents. Well, this is one branch here. So all of this branch, I could call this current I1. Over here, maybe there's some current flowing this way. I could call that I3. Maybe here is another current. I could call that I2. Here's another current. I could call that I4. And maybe there's a last current here, I5. Notice there would be 5 different possible branches of this circuit. Each one could have its own current. And then what I could do is I could write down a system of equations that govern these 3 loops and 1, 2 junctions. I'll call this junction 2 and junction 1. and we can come up with a set of rules that relates the voltages as you go around loops and the junctions as you go in and out of, and the currents as you go in and out of junctions. Think about this. You know from experience, if you go, or from what I've been saying, if you go all the way around the loop, change in voltage, if you go all the way around a loop in a circuit, the change in voltage around the entire loop.
0.
0. So I could figure out the voltage here, the voltage drop here, the voltage drop there. This would be an IR, this would be an IR, and this would be an E. And then over here, I could do the same thing. And up here, I'd have an IR, an IR, et cetera. And I'll teach you the rules in just a second to get the plus minus signs right. Afterwards, think about this. If you had 6 gallons of water flowing in here, wouldn't you need 6 gallons of water flowing out of it? Yeah, that seems reasonable. So what we say is current into a junction has to equal current flowing out. Otherwise, charges would be piling up here and this thing would explode. Circuits don't do that usually, hopefully. All right. So what are the rules that govern these new? And so we can actually, and even though this seems more complex, it's going to feel very satisfying because you no longer have to remember the series and parallel rules for these complicated circuits. You just say, well, what do I do? Let's take a look at it. All right. Go ahead, Rye.
Just for like my understanding of it, I guess, could we also say there's more than just those 3 loops that you pointed out?
You could.
Okay.
But, so let's go back to there. Okay, so by the way, the rules that govern this, if you want to start reading through it, this is shown on page 125. The rules that govern the circuit that I just showed are on page 125. Now, in order to answer Ryan's question, I'm going to get back to the circuit here. Okay, one could argue, I'm running out of markers here, but take a look. Couldn't you also go this way, Rye?
Yeah, that's kind of the thing that I was thinking, you know.
And you could do
these.
that. Now, what I have learned from experience is in order, it turns out it's easy to make equations from these that are not independent. So for example, if you write down an equation that's related to this loop and this dotted red line loop and this green loop, you only get 2 equations out of that, even though you did the work writing down 3. Why is that? Because this loop plus that loop, equation-wise, gives you this outer loop. And so what we see is this particular circuit has 3 interior loops. That means there are only 3 linearly independent loop equations based off the rules I'm about to show you. That probably doesn't make a lot of sense, but there
No,
are
that totally
many,
makes sense.
there are other ways to do this, but I know from experience, if I want to stay organized and get the answers right in a timely manner, this is the way I would recommend.
Okay,
cool?
so it's about finding those loops that are independent.
Yeah. So you could do this. Check this, right? You could do this loop, and then this loop. Those 3 loops would be independent, but then you wouldn't bother with the green or the blue one. Again, so this loop, and this loop. But then these 2 would be contained inside those 3. All right, so let's take a look at this one. Let me show you the rules here. Whoops, oh, I forgot to screen share. Let's make this bigger. All right, and so here are the rules, again, on page 125 in the book. So we call this KVL. That stands for Kirchhoff's voltage laws. And KCL, Kirchhoff's current laws. Now, engineers might have a slightly different sign convention. I can't help it if engineers are weird. Okay, we're going to use the physics convention, right? Because this was basically conservation of charge So this came from physics principles. So we're going to use these physics principles to understand this. So notice this. I cannot stress this enough. The direction of the loop and the direction of the current matters. Okay, so it's a lot like having a coordinate system, X, Y, and your acceleration, right? If the arrows match or don't match, that affects the signs. G was a magnitude, and then the signs of the arrowheads would give you a sign in an equation. Similar here. Okay, so notice, we know that the plus terminal of the battery is on the long plate. Okay, so if the loop direction exits on a plus of a battery, you're going to add voltage of the battery. If for some reason you exit on the minus terminal, you're going to subtract that. So if I was going this way, I would say plus 1.5 volts for this battery. If my loop happens to go this way, this one I would say negative 1.5 volts, or whatever the voltage of the battery is. Okay. Now, if you have a resistor, I know from experience, we haven't been worried about the signs too much. All day long, we've been saying delta V across a resistor is IR, right? So the voltage across a resistor. And now what we're saying is, if your current is flowing the same way, subtract IR. And if you're going opposite directions, you add IR for that resistor, okay? And the idea is, you can kind of think of it like this. If your loop is going with the battery, batteries help produce the current. So you end on the plus plate, you add the voltage. With resistors, they tend to drain energy out of the system. So if your current and loop are going the same way, it's effectively draining things. That's why you need the minus sign. Now, let's use this BS example I drew up on the board. And then finally, I just want to point this. The current in equals the current out, or you could say the ins minus the outs equals 0. So these two equations say the same thing. Input equals output. So notice in this picture, 1 and 2 are going in, and we see 3. And 4 was also going in. So 3 was going out. Sorry about that. So notice we have 1, 2, and 4. They're all going in. So they're all the ins have to equal the outs. And so notice you could just move this one to the other side, and it gets a minus sign. I don't care which one of these things you use. I usually use the upper one and then immediately rewrite it to this. That's just what I do. So if you want to, you could do ins minus outs and just skip that step. But for some reason, it's easier for me to think that fluid in equals fluid out. Okay. All right. Let's look at this one and see how these rules apply. All right. So let's take a look. I'm going to start with loop 1, and I'm going to do that one for you. In loop 1, you pick a starting spot, and these dotted lines are kind of confusing me, so ignore the red dotted lines here, okay? Sorry I drew that on there. That's kind of good.
We can barely see them.
Yeah, I kind of got most of them out of there. All right, that's good enough, right? Okay, so in this case, now we're just doing this loop right here. So I'm going to pick a starting spot. It doesn't matter where you start, but why not just start somewhere at the bottom and go around? So I'm going to pick start. So as I go, I'm going this way. Should I add or subtract the voltage of this battery? Well, I'm going, look at my loop direction. I'm going with the plus plate. So I would say positive E1 for battery number 1. So maybe I'll say this has E1 and this one over here has E2. Different voltages. Next, I get to this resistor. Careful, my loop direction is going this way. My current is going the same way. Would I add or subtract I1, R1? Loop, current, same way. Sorry, what was that?
Subtract?
Yep. Minus I1, R1. Now, loop 1, I'm going to go down here. Is it going to be plus I2R2 or minus I2R2? The loop is going the same way, minus. Nothing here, nothing here, nothing here, nothing here, back to home. Once I get back to home, what's the total change in voltage around a loop?
0.
0.
So this equals 0. Don't forget to write this right here. Everybody, I see this on tests a lot of times. They forget to write equal 0. And I'm like, oh, that's not an equation. I said write an equation. So on Canvas, you won't have that trouble because I think I wrote out every possible equation and you just have to pick the right one. Anyways, all right. So
Would the currents be the same too right now? The I1, I2? Would they just
we
be
don't
I?
know that
Okay.
because it's not the same pipe. Do you agree? It's not the same branch. Anytime you have a junction, the currents can change.
Okay, yeah, I get it.
But I could tell you this. Do you agree this is I1 up here?
Yeah.
Same pipe, same pipe, same pipe. So I do know right down here, this is also I1 flowing this way. Do you agree?
Yeah.
So that is the same. Yeah. Oh, look at this one. I don't know what the current is right here. There could be a current right here too. Do you see that? We might actually have a current here, even though there's no resistor there. I'll call that I6. And notice I5 is going this way. I'm just showing you some of the same ones here. Let me get closer here just so it's a little more clear. All right, so even though there's no resistor there, there could be a current because these two are going to have to add together to make this one, and then it's going to split up again. Ah! All right, so let's keep going. So let's see. How about loop 2? This one's going to be a little trickier. Even though there's no batteries, we could still do this rule. So I'm going to pick a starting spot. How about junction 1? I'm going to start at junction 1, or actually I'll start down here at the bottom. So notice this, we're going up this way. Should I add or subtract I2R2? If I start here, add.
Can I ask why you chose that direction?
It's totally random. You could choose any direction you want.
Okay.
Just like a momentum problem from chapter 9, you could pick whatever directions you want. And if you get it wrong, at the end of the problem, you just be like, oh, if I get a negative number, it must be pointing the other way. So you could choose the loop directions arbitrarily. You could choose the current directions arbitrarily. Usually we know that current leaves a plus terminal of the battery and goes outwards. Now up here, I really have no clue if this is going to be flowing to the right or to the left in this resistor. It depends on which battery is bigger and which resistors are bigger, and these resistances, it's very complicated. So there's no way to know in general which way current should flow. So rather than overthink it, you just slap some arrows on there, draw it, and write it out, and the answer should work out the same no matter which way you draw it. Is that good on that? Cool. All right, so somebody said this was negative, right? Because I'm going, oh wait, positive, because I'm going loop direction against the current. Here, this would be minus I3R3. Then going this way, minus I4R4 equals 0 because I'm back to home. Don't forget the equals 0. I'll go ahead and lay down loop 3 here.
Just a really quick question. This is just something
What
you
think
drew
it
up.
should be. Yeah, go for it.
This isn't a.
I just made this up. This isn't in the workbook, but they all look the same.
Okay, yeah.
Yeah, they're all the same. The idea is I give you some ugly looking circuit. You're like, okay, I can't tell if it's series or parallel. Rather than overthink it, I'm just going to do some loops, write some junctions, and figure it out that way rather than deal with series and parallel rules. Of course, even better would be to learn how to use PSpice, which is better than Tinkercad. And then you just draw the circuit in PSpice and hit play. But you don't get that option. Well, actually, I guess you do. It's an online class. If you want to learn, I don't recommend that. That's PSpice is heavy duty. It's heavy lifting. But if you could do it with Tinkercad and that helps you answer questions, I'm fine. I don't care. You could use that all semester long this semester. Yeah. That said, I think you'll find algebra is faster than Tinkercad. All right.
So that brings up another question then. Are you, I mean, because you brought this up because of that little triangle thing. Are you saying this works even without the triangle, like just our regular series and parallel stuff?
Yeah, this works with a regular loop of circuit. This works. So these rules are these loop current rules are conservation of voltage and conservation of energy and conservation of charge. And so these things are fundamental. They work whether you have one loop, two loops, a million loops, etc. So these rules are fundamental, and all the electrical engineering rules that you learn later are based off this principle. So this is a fundamental physics truth, and it's just a weird way of writing it. Conservation of energy, and yeah. Is that good? All right. So if you've already beat me to loop 3, I guess I'll start right here. So I'm going to get, notice I6 is here, but there's no resistor, so I don't get a term in my energy equation, right? There's no resistor that's using up that energy. That's fine. It's possible. I go up this way. It looks like I'm going to get plus I4R4. Plus I5R5. How about here? What do I get when I go this way?
Minus.
Minus E2. Back to home equals 0. So here's something that you might notice. What if you had picked your loop the other way? Doesn't that just flip all these signs? So if you draw your loops opposite than I do on a Canvas quiz, and you notice every single sign that you have is negative, that means you and I wrote the same equation. So in the Canvas quiz for this chapter, I literally put some loops up with arrows like this and just see if you could do exactly what we just did and follow the rules. And I said, remember, if you get a minus sign for every single term, your equation is the same as my equation. I remind you of that in the question. But hopefully you could do this, and it's going to be on a quiz, right? It's just, can you write down conservation of energy for a circuit? Hopefully that's not too bad. And hopefully there's no frickin' typos. Oh my gosh. Anyways, yeah. All right.
I have a question.
Yep.
Another one. Sorry.
Yep. No, go
regarding
for it.
regarding these loops. So you said the direction of L3 whatever is arbitrary. You could write it any way, and you also said like the same thing about the currents.
Yes.
Now, in our equations, our system of equations, if you draw L3 one way and you just flip, like let's just say I5, right?
Yep.
That would make our system of equations like wrong, quote unquote, I guess, because
No,
it would only flip
it
those
would still be
things.
correct.
Or
What
is
you
that
would
when
get
we're given
is
values?
So what would happen is, in the real world, when you get down to an answer, you would have a minus sign in your answer relative to me. And what I haven't gotten to yet is, at the end of these problems, you are required to do one step of interpretation. You are supposed to know at the end of these problems, if you figure out the currents and it has a negative sign, that tells you I drew my arrow the wrong way. And so if for some reason you draw a current the wrong way, regardless of how you draw the loop, at the end of the problem, you'll get a negative sign in front of that current somehow. And that just tells you, oh, I drew it the wrong way. Who cares?
Okay, so in the end of things, all of your currents should be positive, and if you get a negative, that's what you're saying is you should just
Yes,
you drew
that
it the
just
wrong
means
way.
you drew it the wrong way. And what I did is,
Okay.
in the solutions, I deliberately drew some the wrong way so you would experience that. And then in some problems, it's impossible to tell without doing all the work first. So why worry about it? And yeah, and some of these I actually did with numbers so you can work them out. Is that cool?
Okay.
And
Yeah,
one of these,
yeah, that's
yeah. Okay. So now comes the other big thing. All right. And this is on a quiz question too. All right. So this should be some of the easier quiz questions you get. I want to ask, how many unknown currents do you see here?
Six.
How many unknown currents did I label? 6. How many equations do I get here?
3.
3. How many more equations do I need to figure out those unknown currents?
3.
3. The idea, and so this is a straight up Canvas question. I'll give you some crazy ass circuit and say, how many loop equations should you write down? That is, always look at the interior loops. So you get one loop equation from each interior loop and no more. Why? Because they don't end up being linearly independent. So here there's 1, 2, 3 loops. There's 1, 2, 3, 4, 5, 6 currents. I need 3 more equations. I get those from the junctions. Here's junction 1, junction 2. How about I call this puppy down here junction 3? So I know I don't need to do junction 4 because I already have 6 equations if I do 1, 2, 3. So let's write down junction 1, junction 2, and junction 3. And I'll get some more space here, just a second. Okay, it's going to be a little tight. Okay, sorry, that's...
A really quick question. If R2 was the combination of 2 parallel resistors, and that's how it was drawn as 2 parallel resistors, would we first want to put those parallel resistors into one resistor and then do our loop?
That's a good question. And so it would be your choice. I can tell you, if it's easy to combine 2 resistors and reduce the number of loops and junctions, that might be a good idea. Now, on the other hand, as the circuits get more and more complex, it's probably better to draw them exactly as they are and just take the time to draw those extra loops. Because what would happen is it would be one really easy equation that you add. It would be I1, it'd be...
Oh, yeah, that's right, yeah.
Because it'd be I2 R2A minus I2 R2. It's kind of like 6 of one, half a dozen of the other. Yeah. So absolutely, you can do a mix of series parallel combos and KVL KCL. So again, this is Kirchhoff's voltage law, KVL, and Kirchhoff's current laws down here, KCL. So, all right, that said, junction 1, ins equal the outs. I1 is 2 plus 3. Junction 2, I3 plus I5 are coming in, I4 going out. Right? So again, the ins equal the outs. And here's a tip. Always do these problems the same way. If you're going to write these equations, ins equal the outs, always put the ins on the left side and the outs on the right side. Do you have to? No. But when you go to check your work, you're going to appreciate that. If you always do everything the same way, if you always start at the bottom and always just go around clockwise, like notice here, I always did all of my loops clockwise, just so I'm not thinking. I'm always going the same way. And my currents are always just kind of going that way or down, right? And when I do that, my problems start to look the same. I make fewer typos. You make one typo in a system of 6 equations. You miss one minus sign. All right. So J3 right here. I think ins equal outs would be what? I6 in, 1 and 5 going out. Now, this is a particularly hard one. This is probably harder than any final exam question you're going to get here. But this you can see that you could do this pretty much indefinitely and just keep cruising along and write these all day. So one of the things that you want to get used to, and I think what I did on the I don't remember exactly, but I know one of them was literally, I just did a counting question. Can you count the number of junction and loop equations you need? So one of the questions is literally, how many loop equations do I need? How many junctions do I need? Another question is write down KVL for one particular loop that I've already labeled, just to see if you could follow the rules. And then I think there's one question where you actually have to do the math. And the idea is I made that one worth a little bit less, even though it's more work. So the idea is you could kind of get partial credit for those earlier parts. So I think you'll actually appreciate that, even though the one that's worth the least or whatever is the most work. it's also the one you're most likely to lose entirely and get a 0 on. So that's how I decided to go with that. And I'm not, trying to be tricky here. This is exactly what's coming on your quiz when you get to there. And then there's some stuff with RC circuits as well. All right, so there's this one.
Can I ask a question really quick?
Yeah, go for it.
So for so like let's say on the final, could something look like you could give us, let's say like, I don't know, like so many values for something, and then you have to determine like one value from that circuit?
Take a look. I mean? Here's an example right here.
Yeah, okay, exactly.
So I could say, I could say, here, figure out I3. Now, I just want to point out, here's one that kind of Nick was just talking about. I could just take these two resistors and put them in parallel and figure this out. You could do this without doing KVL. However, this is a good one to start with and verify that you could do this with KVL and get the same answer as series parallel rules and show that it works. This one was pretty funny. I didn't mean to do it, and it turns out it's kind of a mathematical joke. So you'll just have to do that one to see what I mean. But the idea is, with these ones, I write down all the loop directions and all the current directions for you and ask you to check your math. Now, getting to your question, what might a final exam question look like? Maybe it looks like this one or this one, where I stop drawing the loops for you, and you know that any loop direction you draw and any current direction you draw should work out. And so notice I help give you some problems where you could practice how many loop equations should you use, how many current. So these are questions that should look very similar to your quiz questions. Is that starting to give you an idea? And I might say, give me the current through resistor 2R rather than all of them.
Yeah, no, that's perfect. Thank you.
Yep. Okay. Yeah, it's pretty crazy. And there's some, now look at this one. I think this is a really good question, right? Because you want to avoid this process if it's easy. Sort of like what Nick was saying, if you could do series parallel rules, they are better. So take a look at this circuit. Which one can you do series parallel? Which one can you do? Which one do you have to do KVL, KCL, or do they both require it? So circuits 1 and 2, oh, that's supposed to be circuit 1 and 2. I don't know why that did that. Let me write that down. Always something.
So if we find a typo in the answer key or in the book, do you want us to email?
Yeah, just send me an email and I'll fix it eventually.
Okay.
Yeah, just anything. Yeah.
Okay.
Yeah, for sure. For sure. No matter how stupid it is, I'll always fix it eventually.
Gotcha.
Yeah, it'll help. It won't help you, but it'll help the next year's class, right? That's how this thing gets done. As you know from writing reports, it's like, there's going to be typos all the time. So the only way you can get it is by just people proofreading your work. What was that? Page 126. And I've been keeping track of some of them and fixing a lot of the typos in the solution as we go. Typos in the solution, you let me know right away and I can fix them before somebody else gets there. All right. So I don't know if you could tell here, but these, you don't need KVL. You could just do these two in series, these two in series, and then do all three in parallel. There's no need to do KVL for the upper circuit. For circuit 2, it looks very similar, but there's just, my brain is locking up. Do KVL. So on this one, do KVL, the lower one. All right. And so, yeah. And notice what, if you want, you could look at the delta star or the delta Y. Sometimes it's written like this, delta Y. You could do that. All right. And let me see, I'm trying to remember. There's a bunch in the chat here. Elephant. Something like that. Yeah. Yeah. All right. Let me do this. Annotate, clear. All right, there's something else I want to show you before we get out of here. And I'm trying to remember which problem it is. Is it this one? Let me look at the solutions for 27.14. Oh man, this 27.10 is super fun. You guys have got to see that one. That is crazy. Turns out electrical, there's some weird stuff. Infinite chain resistors. And yeah, I'll just let you read that later. Ladder circuits. These are actually used all the time in electrical engineering, ladder circuits for AD converters and stuff. And yeah. Okay. Oh gosh. Is this the one? Sorry, no. Yeah, okay. So notice here, I just labeled it and did some stuff here. So you don't have to use the same ones as me. So somebody was asking, what if I use different things than you? Well, you're not going to be able to check until you get down to the answers. So the idea here is if you did this a different way than me, you should be able to get all the same answers. Oh, here they are. So once I get these answers, you could get all of these other answers. Once you get one of them, you work your way backwards. So there's too little time to do this all in class today, but I do want to show this. Man, 27.14 is a really important problem for everybody. Got that? Put a big star on that one, because I busted my butt on these solutions to make them all kinds of weird little nuggets in here, okay? Really, really important stuff. You could see, and I want to point out the following. I said, here was a trick that I did. In order to get numbers in here, what I did is I pretended the voltage was 1 and each resistor was 1 ohm. And now look at this. Delta V across this thing is 1. So that means if this voltage right here is at 0, this one up here is at 1. And what I'm telling you is I did all this node voltage crap. I mentioned that I did this in the solutions for you. And notice right here, that would imply this voltage is at 0.72. And notice the big difference here. There's a difference between voltages in red and potential differences in blue. The voltage across that resistor is the difference between this number and this number. The voltage across this resistor is the difference between 2. And so when you go through the solutions, this is pretty cool. And there's not a ton of time left, but I do want to show you this. There's a matrix method for this, which some of you that have had Dom's class know already. Check this out. So this is, I mean, this problem is juicy. You do not need to learn the matrix method. Most problems that I use are only going to have 2 loops or 3 loops max. That said, if you wanted to learn this method, so please note, in the solutions, this is optional. But some of you might be so fast at using your graphing calculators or MATLAB, you may actually want to learn this. So the idea is, here were the equations that you get from doing some loops and junctions. I know this is a lot, but just pretend you did some work and you got all these equations. What you do is you rewrite them in this standard form, where it's number times each current, and then put all the voltage over resistance in the other side, right? So the idea is you could do this and you get these here. Well, what you have just done is you created a matrix equation, right? It's a system of linear equations. There's the matrix. The coefficients come from these things up here. So this matrix times this vector, this column vector, gives you these equations, or the left side of it. And then notice this right here is that. So if you're into matrices, good for you. Now, I even wrote how you could do this in your graphing calculator. So if you're wanting to use your graphing calculator to do these problems, what you do is you say, this is the matrix, and you type it in. Then you write down X is the current vector, and then B is here, and you could do A inverse B. And that will punch out everything. But notice this warning down here. So I know I'm kind of going really fast on this. We'll probably do one of these problems next time as well. Maybe 2 of them, I don't know, we'll see. But notice, if you get a single minus sign error, everything's wrong. and you have nothing right and there's no work to show for it. So to reduce the probability, do this. So maybe what you should do is go over 27.14 with the solutions very, 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 very carefully. I don't know. I've been talking a lot here and not letting you guys ask questions. My bad. The matrix method is optional. It can be useful. If you don't like it, don't do it. Most of the problems that you're going to do in this class do not require matrix methods. Most of the time, you're only going to have about 3 or 4 equations to solve, not 6. And at some point, taking the time to get it in matrix form is going to take longer than just doing the algebra. That said, the problems I give you in the workbook are bigger so that you have to be stressed out and practice complicated ones. That way the ones on quizzes or test questions are a little easier with just 2 loops or 3 loops. The Canvas quizzes, we talked about that already. I'll check the chat. Yeah. So matrix methods are extremely useful in every branch of science. End statement, full stop. It may not seem like it when you're taking Math 184 and they don't show you all the applications, right? It's just ridiculous how useful matrices are in the real world. Everything you could code in MATLAB. You take a problem that's not linear and you linearize it, then you put some matrices on it. What if you're a CS programmer and you want to talk about rotation matrices for moving something? Yeah, I mean, oh my God, it cannot be stated enough that matrix methods are hugely important. So if you want to learn them, do it. Said if you run out of time and you got to throw something out, you could get by this class without it. All right, that's it. I'm done for the day. You guys are cooked, I'm sure. It's, man, what a weird combination, right? It's like the new content is so exciting and fun, and then the quizzes are so horrible. It's just a weird roller coaster ride in this class, right? Sometimes the labs are interesting and they're just way too much. It's just crazy. That's physics, right? Okay. Now, anybody that has quiz questions is a good time. Did I hit stop?